very pleased. We are very pleased to have a talk by Bob Hough from Stony Brook University, and the title is Random Walk on a Group and the Cutoff Phenomenon.
Okay.
Please.
So it's a pleasure to speak at the Polish Academy. So I'm going to, we have a, here at Stony Brook, we have a hybrid Blackboard set up so that we can talk over Zoom on the Blackboard. So if you have any difficulty understanding me or reading the Blackboard, please complain and I'll try to fix it. But okay, so I'm going to talk about a class of dynamics problems that are governed by random walk in a group. So this is a area of study that was sort of became popular in the 80s, invented by Percy Diaconis and his collaborators. And so and it treats problems in statistical physics as well as other areas. So let me just describe the setup. So G will be a finite or a compact, nilpotent, be one of those adjectives, and mu is a Borel probability measure on G. So I'll be interested in the repeated convolution. So the random walk has log u star n. Repeated convolution is n-fold convolution. So this is a measure f of G1, G2, up to Gn, P2, P1, P2, Gn. So n-fold convolution. So this is the law of the random walk. So I'll be interested in large N statistics. So, for instance, central and local limit theorems, but mixing. And so I'm a hard analyst, and so I'm interested mostly in quantitative estimates. And so I frequently study the convergence of measures in the total duration realm. So I'll just remind you that the distance between two measures is the suit over a measurable A. So in particular, 0 is less than or equal to the distance. 1. So for mixing, consider a convergence to uniformity. So in the case of a finite group, there'll be a stationary measure. The stationary measure typically a uniform measure on the group, and so one of the measures will be the stationary measure, uniform measure, and the other is the law of the walk. And then I'm interested in the asymptotic distance and total variation for large N. So in particular, I care about the mixing time. So find the mixing time. Is the int n, so that distance from uniform. There's uniform. Is less than. So for a long time, while you run the random walk, the total variation distance is close to 1, and so it transitions from 1 to 0. And so I set some arbitrary threshold, say 1 over e, and I check when the when I'm just somewhat mixed is the mixing time. So a phenomenon that was discovered in the 90s is the cutoff phenomenon. But still, roughly the strongest phenomenon studied in this theory. So given a sequence mu n, gn pairs of probability measures mu n on groups gn, this satisfies that's off. If for all epsilon greater than 0, the limit as n goes to infinity. Mu n to the 1 minus epsilon times t mix as the uniform measure gn variation is equal to 1, and the limit is n equals to infinity of u n involved of 1 plus epsilon next as uniform of gn equal to 0. Well, I'm assuming I should say these are aperiodic, which guarantees that they have uniform measure as stationary measure. So, of course, it's random walk. The dynamics are Markovian. So, well, anyway, this is a phenomenon we're interested in. It says that there's sort of a sharp transition to uniformity around the mixing time. Well, many random walks of interest do exhibit the cutoff phenomenon. So, just examples. Riffle shuffles. On a deck of known cards. The famous example, random walk on a hypercube. With standard bases, with steps by standard basis vectors. So randomize one bit at a time. This is a non-example. Is a random walk on Z1 and Z.
May I ask a question?
Yep.
Just to see that I understand, inside the cutoff phenomenon definition, so the T mix, it depends on N, right?
Yeah, that's right.
And also, what is riffle shuffle?
A riffle shuffle? Well, there's the model that I think of. You take a deck of n cards and you split it into two piles according to a binomial distribution. So you take the two piles in your hand and then you start dropping cards, either left or right at each step in order. And so I have my two decks. I'm dropping cards, and I pick the probability of dropping from the left or the right proportional to the number of cards left in the two sides of the in the two piles. So that's a classical model of card shuffling, and it's in the large n limit known to satisfy a cutoff phenomenon. So in particular, a famous theorem of Diaconus, it requires essentially sort of exactly 7 riffle shuffles to mix a deck of 52 cards. So if you do more than 7, then very close to uniform on all 52 factorial orderings, and if you do fewer, then very far away from uniform. So so we'll be interested in statistics that show that that demonstrate that the random walk is not mixed. So in the case of riffle shuffles, you can check that if you haven't that each time you do a riffle shuffle, you start with the deck in order, of course, and if you've only riffle shuffled once, then then you can split the deck into 2 increasing sequences. So so the number of increasing sequences increases with each riffle shuffle, and so before 7 riffle shuffles, there aren't enough increasing. There won't be enough increasing sequences to be a typical permutation. Okay. Well, today I'll mostly be interested in random walks that have some application to statistical physics. So I thought what I would do is describe. I've worked on a number of these models, and so I thought I would sort of give you just a highlight of each model, and then explain how one of the analyses of the walks works at the end. So I'll first describe a number of models, and then I'll explain how one of them works. Okay. So the first one is a cat's random walk. So in the cat's random walk, you have a number of particles. P1, P2, and velocities. Of V1, V2, Vn. And these make pairwise random collisions. On preserving energy. So it's a statistical physics model, and so we'll neglect the conservation of momentum, but retain conservation of energy. And so what that means is that so a step in the walk. So choose two particles at random. Say PI. Okay. and update, and then choose a random angle. In 0 to 2 pi. And update so vi prime is equal to cosine theta vi plus sine theta bj, and bj prime is equal to minus sine theta vi plus cosine theta bj. So the two particles update to a pair of two new velocities, vi prime and bj prime, following their collision. So so this is a random walk. On the special orthogonal group SO and generated by rotations. Well, a simplified model of this random walk has been studied, but the random walk on SON is still its analysis is still sort of an open problem as to the asymptotic mixing time, whether or not it has a cutoff phenomenon, etc. But with a co-author, I made to completely solve a mean field version.
Okay, what is the geometric intuition? What is going on here? Could you please explain?
Yeah, so this sort of rotation between the velocities means that the mean square of the velocities is the sum of the mean squares of the velocities preserved. So energy is preserved by the system. So yeah, so it's a model of collisions among particles in which the velocities update, in which the energy is preserved, but the momentum may not be.
Okay.
So in the mean field version, the following. Those again, a random walk. On this one. So a step consists of the following. They choose a coordinate 2-plane, a 2-plane, the wedge W uniformly from the Gauss-Monnian. This is a symmetrization of the cat's walk, because in the cat's walk the 2-plane is a coordinate 2-plane, so EI wedge EJ. But now I choose uniformly among all 2 planes according to the Gauss-Monnian, so it's a symmetrization, and then I choose an angle. Theta, according to this probability. Distribution. C. And then I'll rotate. In the wedge W by 2 pi theta. So this random walk has the advantage of being conjugation invariant, and that's a class of random walks which we know how to analyze using the character theory of the groove. There's the characters of conjugation. Right. So with John J. So define sigma theta is a sine. And C squared is equal to the integral of sigma squared theta and dc. There's some statistic regarding our distribution of angle. Then the mean field cat's walk with asymptotic mixing time. Mix is equal to n log n over 2 C of. Okay, so this is the expected same order expected mixing time for the mixing time of the cat's walk, but that one is still open, and the cutoff one also open. Okay.
Excuse me, may I ask a oops?
Yep.
May I ask a question? Because you started with some model with these particles where the energy is conserved, but the momentum not.
Yeah.
And then you wrote mean field version, and what I saw was something else. I don't understand. Are they related?
Oh, yeah, it's a different walk. So it's a symmetrized walk. So so you could think of the cat's walk is choose EI with EJ, coordinate 2 plane. And then rotate by theta. So e.g. So this is a typical generator of the random walk.
Mm-hmm.
And then the symmetrized, the mean field choose W with, or B wedge W uniformly in the Grassmannian. Of the planes. So of course, there are only n choose two coordinate two planes, but there's a continuum of 2 points in the Grassmannian. So this is a symmetrized version. So you can so it's conjugation invariant. And so we can study it in the characters. So as part of this paper, we developed a method of studying the characters of the orthogonal group using oscillatory integrals. And so using the oscillatory integral, we were able to give very strong estimates for the characters for this measure, the Fourier transform of this measure in the characters. So, okay, but I won't say too much more because I want to describe a couple further models for you. I'll just give you a flavor of the type of problems that we study. Okay, so the second model is called the abelian sandpile model. Again, this is a model that originated in the 80s. I should say this mean field version is the proven vector. Rosenthal. Rosenthal had conjectured the okay. The abelian sandpile model is a statistical physical. So there's a graph for the graph. So G is equal to V. In our case, I'll study the torus Tm is the mod MC on nearest neighbor edges. So some node is sync. So in this model, this model is also called chip firing. So there are a number of chips at each node. So in the chips state is sigma from minus the sync to the positive integers. The number is the number of chips per site. So for instance, this site has 3 chips. This one has 3, this one has 1, this has 1, 2, 2, 1, the sync. This is a very popular model. It originated in the 80s, and there are now maybe more than 10,000 papers about it on Google Scholar. It's very well studied. So a state sigma is called stable if sigma v is strictly less than or equal to v for all v. So if unstable, so if some node has at least as many the degree number of chips as the node, the site can topple. Of passing one. Okay. So you can have chains of topplings. So people talk about. So the model is so say that I added a chip here. So there were 4, and then I could topple and pass one chip to each neighbor. Okay, and then this would have 0. Okay, and so as you can imagine, this site initially had 3. I add a chip there, and now has 4 passes one to each neighbor. The neighbors could have 3. And so triggers further topplings at the neighboring sites until you reach a new stable configuration. So that sequence of topplings is called an avalanche, and the sequence of topplings is called an avalanche. Following and adding a node. So currently, people are very interested in the statistics of avalanches. They're expected to satisfy a power law, but are not going to do so. But okay. So so any chip that falls in the sink, it leaves the model. Okay, so you can they'll need something called the Laplacian. Which is delta prime.
Robert, sorry, I did not understand. So it's possible to add chips to the configurations?
You can add chips to the configuration. You can drop a chip on some point and add the number of chips at the site.
So it also happens at random?
Yeah, so there'll be a driven dynamics in which you drop chips at random and then see what happens. So this is found by delete. According to this. The dynamics starting from a stable state. At a uniform. At a uniform random site. And perform all topplings. It's all stable.
Excuse me, could you explain what is reduced Laplacian? I didn't understand. What do you mean by delete row column according to?
So you can think of, so this is just how we're working on finite graphs, and so the Laplacian is a matrix. So it's a linear operator on functions on the graph, and so you can think of it as just a matrix operator. And so the reduced Laplacian is found by one of the, so there's a, so if you have this Laplacian, there's a matrix, and then so say the last, so in this V by V matrix, say the last row, the last column correspond to the sync node, then the reduced Laplacian I find by deleting this row and delete this column. It's a new square matrix, but it's a one size column. So the mixing of this dynamics study on the torus has been an open problem since I guess basically since the 80s. So recently resolved by myself and co-authors, and so so it uses a random walk-on group. So I'll explain how that works. So so it's Markovian. Dynamics. So there are the recurrent states, say stable states, are strict S, and the recurrent states are strict G. So there's a description of the recurrent states. So so the full node, the full state sigma of V is identical equal to 3. So the largest number of states you can have at a stable node is 3 on the torus. The degree is 4, so the 3. This is obviously current. So given any state, you could so given any state in the model, you could add chips to it deterministically to reach the full state. And there's some positive probability of doing so. So that since that occurs in point often, forces the state to be recurrent. So so the false state is recurrent plus all states. Well, state. So not all stable states can be reached from the full state. So it's known that the recurrent states have a abelian group structure. This is called the sandpile group. We'll study the people conjecture things like Cohen-Lindstrom statistics for it. Its structure is a Z to the Tm minus 0, quotient by the reduced Laplacian, Z to the Tm Well, I won't prove the group structure for you during this talk, but I'll just sort of explain generally why you would think this was the case. So you could look at z to the tm -0, 0 as all states that you could think of having integer chips at each site. And toppling corresponds to, you could have an odometer function, so a number of topples at each site, and then apply the reduced Laplacian to that odometer function. And that will tell you the change in the number of chips at that site. And so, yeah, so if you quotient by all the changes that can occur to the state, and you start with all the states, then that quotient gives you the all the recurrent states. Driving measure. Is mu n is 1 for squared. So you can, if you drop the chip on the sink, then nothing happens. Otherwise, you sum x and tm minus the sink e sub x. The standard basis vector. The standard basis vector at x adds one chip at the site x and leaves the remaining states alone. So this gives you a driving measure for random walk dynamics on recurrent states. Let's tell you the theorem that we proved. It makes the dynamics on recurrent states a random walk kind of group. But in this case, an abelian group. So again, the measure is diagonalized for the characters of the group. For the Fourier transform. So, myself and Daniel Garrison. Final review. Communication fixed. There's a constant. C0 is a 0.34866 1 7 4. Well, one more significant digit. Such that t x is equal to c0 times n squared log m. And the cutoff in the dynamics have a cutoff phenomenon. In total radiation. Mixing term. Okay, so I have a follow-up paper with a student. I'll just sort of summarize the theorem. So it extends the theorem to prove are arbitrary tiling graphs. So periodic plane or space. So e.g. hex you take a tiling this and take a growing periodic piece of the tiling or triangular so arbitrary convention. No different geometries, different dimensions, and then we can handle either we call periodic or open boundary. Have a cutoff phenomenon. I'll have a cutoff phenomenon. So spectral factors. Which are related to the spectral gap. There's some factor of dimension. So there's a factor. So several things go into the spectral factor, but so spectral factor is part of the spectral gap. Govern. Asymptotic. So it's proportional to the dimension in the spectral gap. But it can be the case that the mixed time is governed by the by one of the lower codimension boundaries. In that case, the spectral factor includes the dimension of the codimension of the controlling boundary. So the corollaries of our work is in 2 dimensions. After tilings satisfying Fourier function symmetry. asymptotic mixing time is independent of the boundary condition. And another corollary is that it's slower for open boundary. The D4 lattice the D4 lattice is the densest lattice packing in 4 dimensions. And so there's a lattice that has a lot of symmetries. And in fact, you do sandpiles on growing pieces of this lattice. And if you make a periodic boundary, the mixing time is asymptotically faster than if you have an open boundary. And in fact, in this case, for the open boundary, the mixing, instead of the mixing being controlled by the bulk of the graph, it's controlled by the codimension 1 boundary. So the 3-dimensional one, the 3-dimensional boundary. So it mixes slower on the boundary than in the bulk. Okay. So the 15 puzzle is a children's toy. With number of tiles. And 1 empty tile. So in this puzzle, maybe many of you played with these puzzles when you were growing up as a child. So there's a missing tile. And so what you can do is you can swap a position of a neighbor. So for instance, you can move the missing tile to position 12. And this one will become empty. 12. All right, so you can move the missing tile around in the puzzle. So in general, so I'll study a periodic boundary. So we study n by n a board of periodic boundaries. N squared minus 1 number of tiles. Oh, 1 missing tile. And dynamics. Swap the missing tiles position. Oh, with the nearest, with an 8. And then we're interested in the so how many random moves it takes to randomize such a puzzle. So the one thing that you can notice is the missing tile. It does a swap with a neighbor, but on this torus, it's if you want to consider the missing tiles position and not the other number of tiles, then it's doing simple random walk around the board. So the missing tile moves fast in the puzzle, whereas the other tiles mostly only occasionally move. There's sort of one distinguished tile which moves very fast, and the other ones are slow. So there's a way of describing this as a random walk kind of group. So the states torus Tn, which is Z and Z times a symmetric group Sn squared minus 1. So the first coordinate is the location of the asymptotic. The second coordinate is the relative position tiles. Missing tile. Okay. So that means that in the first coordinate, we'll be doing simple random walk if you ignore the position of the main tiles. And then on the second coordinate, we'll be doing a random walk on a symmetric group. With a few generators. There's a class of random walk which is currently actively being studied. It's a random walk on a symmetric type group with a small number of generators. So the moves is right, which is so the missing tile moves right by 1, 0, and there's a transition to R, and then left, which is R inverse, and then up, which is 1, and some permutation, and down, which is up inverse. So each permutation sigma star consists. Well, I look at the pieces relative to the empty tile. So you can think, say I shift the empty tile up, then relative to it, all the pieces, besides in the column of the empty tile, all the other columns do a cycle down. So n minus 1 n cycles. So all the other columns besides the column of the empty tile do an n cycle. And then one in the column of the empty tile, you do n minus 1 cycle. Okay, so this is the type of permutation that's driving the random walk. The dynamics. Random walk. Mu, which is so I make it say 1/5 lazy. Observation with probability 5th. Otherwise, I do one of the rules. competitor, a student. Got the two. So what? F from n function. So and squared one puzzle makes random moves. After end of the fourth and moves the number of tiles in their original position. Converges to Poisson 1. That's it. If and only if. So the number of, you take a sequence of puzzles and by puzzles and do random moves on them and sample the puzzle after end of the fourth times f of n moves. So if the number of moves grows compared to end of the fourth, then the number of tiles in their original position converges to Poisson 1 as n tends to infinity. And if it remains bounded compared to end of the fourth, then there's in fact not a convergence in distribution to Poisson 1. So this theorem is significant because one of the distinguishing statistics of a random permutation is that the number of fixed points of a random permutation, on the symmetric group Sn, converges to Poisson 1 as n tends to infinity. So this is a fixed point statistic. So this is due to Morris and Raymer, and proved independently by myself and the total variation. Let's see. This one puzzle is order. So compared to the Poisson 1 statistic, the XR factor of log n. So these two theorems disprove a heuristic of Diaconus. Percy Diaconus is one of the founding fathers of random walking group, and he so this random walk problem is due to him, but in which predicts that fixed points are a distinguishing statistic for random walk on symmetric groups. So determining the convergence. So this Poisson one theorem is roughly this Poisson one theorem governs the mixing behavior of the random walk on the symmetric group in the lowest dimensional representations. So roughly representations of the symmetric group correspond to a tableau. So say Sn. Say this is K and this is n minus K. So it's where you have a small piece and then a tail. So K fixed. So for each so hold this piece fixed and let n tend to infinity. So if you study all the representations of this nature and their transpose, then you can and you understand the mixing in all of these representations, then you obtain the Poisson one theorem. Whereas the mixing on the whole group requires all the representations of the group.
May I ask how essential for the mixing time is the periodicity assumption?
Well, it's not too essential. So if it's so that's one reason that we include the holding. So the probably say like in this case the probably 1/5 with the identity is that it eliminates a condition of periodicity. If you have periodicity, then you can do something like then you can do an average to eliminate it, or then just the measure that you converge to will also be periodic, depend on the step. So if you want a fixed measure, then you can do some further averaging. Okay, so then there's one further model that I want to discuss. A recent theorem of Thomas. And LCNS. So look at the upper triangular group. The double group. And I'll let mu uniform let's say on matrices of the following form. So so one entry, we get my about the diagonal. Okay, so then we're going to study projections of this random walk plot P. So I'm interested in this coordinate, the central coordinate. So z of matrix 1, 1. I'm sorry about the entries. See? So the central coordinate. And I'm interested in the mixing of just the central coordinate. Then the P is a prime. So our theorem says the following. So there exists C greater than 0, such that SP tends to infinity and some x plus p. We can roll that times. The measure associated with the central coordinate equal to x. So it's stationary distribution 1 over p. So I take the difference. This is bounded by of minus c times n over p with 2 over n minus 1. So the 2 over n minus 1 moves are sufficient for mixing of the central coordinate. So if you're looking at, so you can take quotients and then study the mixing of the various coordinates. So then immediately above the diagonal, it's like a abelian walk on a cycle. And so all of these require p squared steps to mix. And then the next level is p. And the next level p to the 2/3. Then p to the 1/2, etc. So as you move up in the matrix, the coordinates mix faster. So we also prove a local limit theorem on the Heisenberg, which resolves the conjecture of Fourier. Well, I'll just explain ideas in the proof. So define a map M from Z to the n minus 1. Vector. So map this vector onto of the matrix, which is upper triangular with v1 through vn minus 1 on the first diagonal and zeros everywhere else. Okay, so for this type of matrix, I can just write up in coordinates the product. This is the central coordinate. The product of n such matrices. And you can just check this is equal to sum 1 less than or equal to I1, less than I2, up to I. V I1, V I2, V I-1. This is a high degree tensor. A dual tensor. Is equal to sum 1 less than equal to 1 less than 2. E1 answer E answer E I-1. Okay. So so Z is the product. Is equal to and applied to V1, V2. And then by Cauchy-Schwarz. And parse it all. You're going to express the sum. Is less than or equal to. So the Cauchy-Schwarz and square plus 0 is not equal to C but B. Do that. Let's see. So the L2 norm on the Fourier side. Of course, this is a mean 0, and so I've limited the 0 frequency, but otherwise, once I do Cauchy-Schwarz, it's parsable. Here on nu hat alpha is equal to a sum n and z e minus alpha of n to n, and here minus alpha of x. Okay, the Fourier transform of the measure. We keep up proposition. There's a C. 0 for all and 1 all 0 less than C. The Fourier transform the and U. So this is all the coordinates are simple for mu. This way, this type of bound. Here, this is CNN of D1 of DI of DI according to me. And this is this for transfer. Okay. So plugging that into this bound, you obtain the theorem. So I'll just explain quickly how to understand the proposition. We use a word rearrangement so C2 Vn minus 2 acts on words of length K V minus 2 in blocks. So I'll just show n equals okay, so 2 times x Okay, so the way this action works is that tau 1 switches the order of x1 and x2, and then tau 2 switches take x1 and x2 together and swap the order of x2 and x1 with x3 and x4. So if you've applied tau 2, then x3, x4 appear before x2 and x1, and otherwise they appear after. And toggling tau 3 swaps the first half of the chain with the second half of the chain in the word. So anyway, this is a abelian group action on words. Okay, so then we take a large product group action. So GK is equal to C2 to the n minus 2 to the power of n prime, where n prime is equal to the length of the full word divided by k to the n minus 2. So given a long word, let's swap the subwords and then apply C2 to the n minus and separate factors and subword. Okay, so then the characteristic function k of C and this word of vectors is equal to an average over L in CK E minus C of this functional Z and the n L W. So the double average. So there's a first average over words of vectors, and the second average rearranging the words, and a double average. And so by applying the Gowers-Cauchy-Schwarz inequality, I'm running just a minute over time, so just quickly explain how this works. You can bound the characteristic function that you care about, pi k of C and W. Oh, sorry, there should only be a single average because I'm including the difference on W to the 2 million minus 2. So you apply Cauchy-Schwarz n minus 2 times is less than or equal to. So you separate if I Gowers-Cauchy-Schwarz, so there's a separate lengthwise instead of height-wise the factors of C2, and so applying Cauchy, taking one at a time, you can double the number of coordinates in each time, and then and tau s selects between the first or second choice of tau, and so this Gowers-Cauchy-Schwarz quantity I'll call Fk of C and W. So the main discovery is that Fk of C and W. Well, now like an original characteristic function now factors as a product after you apply Gowers-Cauchy-Schwarz. So you lose a bit. So here Fkj, let's see, and W only depends on the J subword. Okay, well, so once you reach this observation, you can conclude. So just like when you have a product of independent random variables, their characteristic function factors as a product. And so once any given term of the product is a little bit small, the whole product is much smaller or exponentially small. So now that you've applied Gowers-Cauchy-Schwarz to this object, the same property that you have for an abelian random walk in which the characteristic function factors the product becomes the case. So yeah, so that's the key idea in the argument. In fact, we have several local limit theorems that refining local limit terms of radar on nilpotent Lie groups, and they use this Gowers-Cauchy-Schwarz technique to study the characteristic function on the nilpotent Lie group using this product factorization. And so what Gowers-Cauchy-Schwarz morally does is in the dual space it applying it in the dual space that morally takes commutators in a time domain, so that if you take enough commutators, you just have an abelian random walk on a projected space. So anyway, that's sort of the main takeaway from our paper and the idea of how the argument works. So maybe I'll stop there and take any questions that you guys have with that.
So thank you very much for this very interesting talk. Are there any questions? I would like to return, if you could explain again. So let's take the 15 puzzle problem, but let's take it in its original form without making it a torus. Are you claiming that the mixing time is the same?
Oh, you know what? Yeah. So yeah, I haven't studied that version of the problem yet. So I haven't studied the boundary conditions. So I'm expecting there's an obvious way of obtaining a upper bound of the same nature, I guess. But yeah, there's still some details to fill in. So yeah, so this sort of like in the sandpile model, we first studied the torus boundary condition, and then studied the open boundary condition, which has with symmetry a little. We've already done the torus boundary condition for the 15 puzzle, but haven't done the reflection boundary or hard boundary condition yet. So that's something we're still.
But what exactly does it give you, this boundary? Why does it simplify?
Yeah, we do quite a bit of a potential function or green function analysis on the torus. So asymptotics for a green function on its discrete torus, and that kind of estimate to control the mixing as the piece moves around. And so the Green's function, well, you just have to study how the Green's function behaves differently on the boundary. So so just yeah, it's just a little bit more refined analysis that needs to be done.
Okay, are there any other questions?
Yeah, we're interested in the uniformity of the dimension. So the cutoff phenomenon is still not known for the puzzle. So we have a way of proving what we think will end up being the correct asymptotic lower bound, but the upper bound is still open. So the cutoff phenomenon not known, expected but not known. So that's something we'd really like to prove. And then interested in the puzzle different. So just like for sandpiles, interested in different geometries, different dimensions. So a more general type of graph. So you don't in particular. So yeah, so there are a couple other models that are somewhat related. So people study something called a lamplighter random walk, in which you have a graph. And there's a light bulb. At each node. And so in this model, you have a random walker who walks around the graph. Here's my walker W. He does simple random walk around the graph. And then when he comes to a node, he flips the light switch on or off. And so that's a model that's very well studied. That's somewhat similar to this 15 puzzle model, in which you have a empty tile moving very fast on the graph, and then there's some local change to the graph behavior, to the decorations at the nodes. So yeah, so that's a related model, and then there's something called the lamplighter. It's very well studied. And then there's something called the interchange process. In the interchange process, you have a token at each node of a graph, and then you just pick neighbors on the graph and swap them. So there's no random walker, just swap the tokens at neighboring nodes. So those are two related models, and they're better studied. So for instance, results for general graphs are known, or higher dimensions, different geometries. Especially in this case, there's a paper of, I guess, Perez, Dimbo, Miller, and I guess one further author, I think Jian Ding, give a lot of uniform estimates and dimension for lamplighters on different tori. So yeah, so we're interested in proving a similar type of theorem, but for the puzzle.
Okay, are there any other questions? Okay, if there are no other questions, let's thank the speaker again.
Okay, thanks very much for having me.
Thank you very much, and Merry